So like often it is the case with computer system design, in particular processor design, cache design is no different in terms of trade-offs. So we have gone through a number of design parameters like cache sizes, block size, associativity, replacement policy. So the question is, what is the right answer for these choices? And the answer often depends upon your target applications that you would like to run and the technology, the processor technology that you're trying to leverage. Processor's clock frequency, how long does it take to go to the main memory, etc., etc. So there's no one right answer for these parameters, but we can come up with a set of design principles that would govern how to choose them. So let's start with some simple questions. Can the block size be not power of 2? Can number of sets be not power of 2? So if you recollect, the way that we define block size impacts the number of bits that we would use in the address. So it is therefore natural to assume that the block size and the number of sets would be a power of 2 because we are going to use X number of bits from the address. And so if you're going to use X number of bits, then you want the number of bytes in the block or the number of sets to be 2 to the power of X bits. Now, the next question is, can the number of ways in a set associative cache be not a power of 2? Though it's uncommon, it is not impossible to design a 3-way set associative cache or a 5-way set associative cache. The way to think about it is, if I had a set number of cache, let's say if I had like 4 sets, which means that I would have defined the number of bits in the set index, right, to be 2. So I would already choose one of these 4 cache sets from the address. Now it's up to me to define how many blocks I want to store in these sets. And it's quite okay to store 3 blocks per set, because then you just need to configure the number of tag comparisons to be 3, right? So it is therefore possible to define set associativity to be not a power of 2, as it doesn't really impact the way that we would configure the caches in terms of utilizing the number of bits and so on and so forth. But oftentimes cache geometry matters when you lay out these structures in a processor chip, and symmetry helps. And with an odd number, symmetry is very hard to achieve. So that's one of the reasons why there is a natural tendency to go for 2 to the power of n associative caches. But it's not rare to see. It is not impossible to implement other types of set associative caches if need be. So I talked about trade-offs. So one of the trade-offs that we have to make is deciding the cache size. So obviously in a processor you have only a limited number of transistors at your disposal. Do you decide to spend them all on caches, or do you reserve them for some other structures, let's say larger branch predictor, right, etc. And so one has to decide what is the cache size that is beneficial to a program. And so you can take a representative set of programs and simulate a variety of cache sizes and observe the hit rate. So what you see is a graph like a simplistic graph that I have shown on the picture here. So you vary the cache size, and then for the applications that you're interested in, you observe the cache hit rate, and then often you'll notice that the curve kind of plateaus out, right? There is an inflection point at which increasing the cache size beyond that point doesn't really help you much. And oftentimes this is the size of the working set of the program that you're analyzing. So working set of a program is the total size of the data that a program accesses in a given time interval, right? And so that obviously is a fuzzy definition, because what should be your interval length? Do you consider 1 second to be an interval or 10 seconds to be an interval? Nevertheless, it's a useful definition, and you can vary the interval length and observe this phenomenon. So if I can draw a graph like this, then I can say, okay, my cache size should really be at the knee of the curve. Now, one downside of having larger caches is I would be investing transistors into that structure, so there is an opportunity cost there. I can take those transistors and use for some other structures like branch predictor, like I was saying. The other issue with larger caches is that it can increase the latency, because if your cache is larger, then you need larger decoders, you need longer wires to get to the data, etc. So the access time of a larger cache is going to be higher than a smaller cache. So we talked about this when we talked about the memory hierarchy. And so oftentimes in modern processors, you have multiple levels of caches to overcome this size versus latency trade-off, where you have this really small but very fast L1 cache, and much larger but slower L2, and then even larger and even slower L3 cache. The second trade-off is the block size. Now, the advantage of a larger block size should be clear now. It's essentially that you will be able to exploit better spatial locality. So if I vary the block size, then you can expect to observe a higher cache hit rate, because you're exploiting more and more spatial locality. But after a point, your program may not have sufficient spatial locality to yield better hit rates, right? And so in fact, you may start observing a decrease in the cache hit rate. Why is that? Well, if I bring a very large cache block into my cache, then I may not utilize all the data before I evict that cache block out. So if you assume that the cache size is a constant, and if you divide up that cache into really large chunks, let's say 2 big chunks, and if I access an address X and you bring in a big chunk of data and you fill it up with this one big chunk, and if I don't really access most of it, right, then I have polluted my cache with all this useless data which I'm never going to access. So you're reducing the effective capacity of your cache by increasing the cache block size, and that's why you see a decrease in the cache hit rate. The other disadvantage of a very large cache block is you may end up consuming extra memory bandwidth. Like I said, you bring in this big cache block from your memory into your cache, and you don't really use all of it, which means that you have consumed your memory bandwidth without really turning it into good use. So the lot of useless data transferred result in wasted memory bandwidth. So finally, we talked about associativity today, where higher associativity reduces the conflict misses, and so you can increase the cache hit rate. Obviously, it's beneficial from that perspective. But again, just like in the case of cache size and block size, there is a law of diminishing return that kicks in, where the cache hit rate stops increasing. It doesn't decrease as badly as we witnessed for block size, because there you're actually polluting the cache. But here, if you just have higher associativity, it just means that you need to do more tag comparisons, and so you may be expending more energy doing those comparisons, but the cache hit rate may not decrease. So smaller associativity means that you would have lower cost because you need to have fewer comparators to do those stack comparisons, and because you need to do fewer comparisons, your access time can also be faster. So again, there is a trade-off between larger associativity yielding higher cache hit rate, but at the same time increasing your cost and latency of your access. And we talked about the fact that associativity need not be a power of 2.